Hello everyone, welcome to the next lecture in the course Remote Sensing Principles and Applications. In the last lecture we discussed and concluded the topic of passive microwave remote sensing or passive microwave radiometry. From this lecture onwards and in the next few lectures we are going to discuss about active microwave remote sensing and especially the imaging radar. First of all, we will quickly recap what is active remote sensing and what is passive remote sensing. We have already discussed this in earlier classes, but just to get a quick recap, I am telling it again. So, in passive remote sensing, the sensor observes passively the energy coming in from the earth, like the sensor is a mere observer of the energy that is coming in from whatever be the source, say earth surface. In active remote sensing, the sensor produces electromagnetic radiation, transmits it towards the target of interest and gets the signal back. So, in active remote sensing, the sensor itself acts as both as source and receiver of electromagnetic radiation, whereas in passive remote sensing the source of electromagnetic radiation is something else. Say in optical remote sensing, in visible and near domain, the source of electromagnetic radiation is the sun. In thermal infrared domain, the source of electromagnetic radiation is the earth surface. So, these are all passive mode, the sensor is not producing any EMR, it is a mere observer. In active mode, the sensor itself will produce electromagnetic radiation and send it. So, what we are going to get introduced to is an active mode of remote sensing, that is the remote sensing system itself will generate electromagnetic radiation, and here we are going to talk about microwave radiation. So, in the range wavelength range of in the order of centimeters. So, the sensor itself will produce electromagnetic microwave waves, microwave radiation, it will transmit towards the earth surface and it will get the signals that are received back from the earth surface. So, what advantages do active remote sensing have over passive remote sensing? In active remote sensing, we can collect data in any time of the day. If you take passive remote sensing, especially the optical, that is visible NIR and SWIR wavelengths, we can collect data only during morning hours when there is or daytime sunlight hours when there is sunlight. During night time we cannot collect data in visible and NIR domain. In thermal it is possible anyway, because earth's emission is going to keep on continuing whether it is day or night. In active remote sensing also it is possible to collect data at any time we want, that is a major advantage, and second is we can control the geometry between the source of EMR, the target of interest and the sensor. That is, in optical mode we have seen that objects will look different based on differing illumination conditions and the sensor viewing conditions. That can be controlled to some extent in active remote sensing. We can decide, especially if we are doing remote sensing from aircraft or something where we can decide the path and everything. It will be possible for us to control, okay, this is that object of interest, we would like to image it from this particular angle at this particular height and everything. We can control it to a good extent, which is completely not in our hand in optical remote sensing. So, this control over the source or target and the sensor geometry is a major advantage in active remote sensing. And also microwave, we have already seen it, microwave provides us complementary information to what we get from optical, like visible and NIR wavelengths. Complementary means in visible and NIR wavelengths we get information about like the chemical composition of it, the structure of the objects within it, discontinuous and all. In microwave remote sensing we will get to know the properties of the land surface which are highly controlled by the electrical and physical nature, like we have already seen it, the dielectric constant will influence the microwave emission. Same thing applies here, the dielectric constant of an object will control the microwave reflectance also. Okay, so the electrical nature of the object, the surface roughness, that is the geometric properties of object, all these things which are complementary information to what we get from optical remote sensing. So, these are all some comparison between active and passive mode of remote sensing, especially in the microwave domain. So, what exactly is active microwave remote sensing? In active microwave remote sensing, what we are going to discuss is like the imaging radar. So, what exactly radar is? Radar is an acronym that stands for radio detection and ranging. So, in the earlier days during like World War and all, this particular technology was used for surveillance of incoming enemy aircrafts. That is, microwave transmitters will be fitted along the borders, city border or country border. They will be transmitting radar pulses continuously. If at all any metallic objects, like aircrafts are normally like metallic objects, if they come, if any kind of aircraft comes within this vicinity of this electromagnetic pulse, that electromagnetic, that is especially the microwave pulse, will be reflected back and it will be received at the radar indicating it. So, these are all some of the earliest uses of radar, and even the nomenclature, like the nomenclature of microwave, the PLSCX band, those uncommon names, those names that does not have like any meaning or physical sense when we just have a look at it. They are also framed during, especially for like strategic purposes. People wanted to designate each frequency using like a secret code. So, they were all actually the secret codes that were used in the olden days for military applications. So, the radar developed, the technology developed for mainly military purposes, but later people realized the civilian applications for which those systems can be used. Say nowadays we use the radar, like ground based radar, for monitoring clouds, for like rainfall forecasting over like a city. Major cities have their like radar systems fitted at certain locations which will be able to monitor the clouds moving in or moving outwards of a city. Or even in airports we have this plan position indicator, like what is indicated in this slide. So, something of this sort will be there, and this will be like indicating okay where an aircraft is. So, this will identify okay here there is an aircraft, here there is an aircraft. We use such a system in airports. Similarly, like our police officers can track the overspeeding vehicles using like a Doppler radar. So, these are some of the examples for which radar is widely used. So, radar is everywhere, which normally we come across or we get to use its application in everyday life, either in direct or indirect form. So, a radar is basically a sensor which will transmit microwaves. Here, even though the acronym stands for radio detection and ranging, like initially when it was like formed with respect to radio waves, which is another much longer wavelengths, but here we will talk about microwaves. Okay. So, we have a system which will produce electromagnetic radiation with a given frequency, and that will transmit the electromagnetic radiation. Then it will receive the signal back. So, most of the radar operations happens by calculating the time taken for this electromagnetic radiation to go and come back. Say it measures the distance between the source of EMR, that is the sensor itself, and the object, that is the earth surface features, by calculating the time taken for this electromagnetic radiation to pass two way. It has to first go, if there is an object it will be reflected back and it will come back. So, the time will be used to calculate the distance, that is one thing, and then the system will also record the incoming power in some form, how much power the system transmitted, how much power it came back. It will measure the power of the incoming signal. The system can also measure the polarization of the electromagnetic wave that is being received. So, polarization is nothing but the orientation in which the electric field is vibrating, right. So, that information can also be saved. So, essentially a radar is it's like sending some signal, measuring it back and calculating the distance, calculating the power and everything, like it will measure all these things to give us some useful information. So, the active microwave sensors or radars, if we talk about like airborne or satellite based systems, they can be either nadir looking or side looking. So, what exactly are these are? Say we have an aircraft or something here, the platform, it will have a radar system. Let us say this is like a nadir looking system. So, this nadir looking system will transmit microwave signals which will move towards the earth surface. Say this is like the terrain, then it will interact with the terrain surface feature. Then once it hits the terrain surface feature, it will go back Based on the time taken, we know the velocity of EMR roughly 2.99 10 power 8 meter per second. So we know this velocity, we can calculate what time it takes for the electromagnetic radiation to travel from here, reach the surface and go back. So that will give us like that, if this distance is d, calculating this time we will calculate 2d, one in the downward direction and one in the upward direction by knowing this velocity and time. From this we can derive the distance between the radar antenna and the ground surface. Essentially, and these are actually height measuring devices or height measuring sensors, or technically we call them as altimeters. Like the class of radars which looks at nadir, like looks exactly at downwards, which measures the distance between them, we call them as altimeters, and we use them for measuring the elevation of various objects on the earth's surface with respect to certain data. Whereas the radar that we use or we are going to see in our class comes under the classification of imaging radar. Like altimeters will provide us X, Y, Z information. They are not imaging systems, they provide like ground elevations for different positions on the earth's surface. Whereas we are going to discuss about imaging radar, which will produce us a 2-dimensional image of the terrain. So the 2-dimensional image of the terrain will be produced by radar that is side looking, not nadir looking. That is, if this is the aircraft platform, the radar will be not looking at some angle away from the nadir. So like this, it will not be looking at nadir like this, it will be looking at an angle away from the nadir. So essentially the imaging radar or side looking radar, we can call it as SLAR, side looking airborne radar, if it is like the radar is carried from a aircraft platform, or SLR, side looking radar basically. So why imaging radars are side looking radars? Basically this is to avoid what is known as a left right ambiguity. That is, let us say we have 2 points here on the ground surface, okay, A and B, both of them are at the same elevation. Okay. So let us say we have a radar that is looking at the nadir, and let us say this is like the center point, the horizontal distance is exactly the same from the center point. Okay, so this is like the center point nadir, and with respect to the nadir, 2 points A and B are exactly located at same horizontal distance, and also they have same vertical elevation above some datum. If this is the case, we know that radar measures basically the distance. So essentially the distance between this point and this point, point A, and similarly point B are one and the same, right, because they form like a similar triangles. So this distance, let us say this is L and L1 and this is L2, then L1 and L2 will be equal. Okay. If these 2 points are exactly at the same horizontal distance from the nadir point and also at the same elevation without any difference. If this happens, then for altimetric purposes that is okay, that is point A has a coordinate xa, ya, it has an elevation of z. Point B, it has a separate planimetric coordinate xb and yb, it again has an elevation z, no problem for us, we can record it and use it. But let us say we need to image them, we have an imaging radar. Let us say we have a house here, we have a tree here, okay, and our system is capable of producing image of both of these. So whenever the range comes in, like it will measure the distance and then it will measure the power that is returned back. Since these two features are different, the power that is returned back will be different. Say this will be the power return will be P1, the power return will be P2. But that once these two will reach the system, both of them will reach at the same time because of the same distance, there will be an ambiguity in the system and there are chances that these two objects are swapped in their horizontal position. By some mistake it is easy to plot this tree here, this point A can be mistakenly taken as tree, this point B can be mistakenly taken as a house. It is possible, this is what we call it as the left right ambiguity. Okay. So, in order to avoid this, say the radar is going to spread in 2 directions, is going to measure the distance, but if we need to produce an image out of it, there are some chances the image points, the ground points may be swapped because both the features are at the same distance. So, there can be a confusion in the radar system. In order to avoid this sort of ambiguity for imaging systems, the imaging radars will work with the principle of side looking. They will not be nadir looking, they will be side looking. Okay. If you are just measuring x, y, z elevation information, no problem, you can do it. Nadir looking is like people will normally do it, altimeters. But for imaging purposes, this may not work for certain circumstances, it may produce some sort of ambiguity. Okay. So, the side looking radar, how it will work, say the radar will be looking at like this, then it will be transmitting the pulses and receiving it back. Hence, if a platform is moving in one particular direction, the image will be created only in one side of the platform. Let us say this is like the satellite, it is moving like this, okay, coming in towards the screen of you. So, let us say the radar is looking something like this. So, this will be the radar will be moving like this. So, only the portion of the terrain that is on the right side of the satellite. So, satellite is moving like this. So, on the right side of the satellite will be imaged. So, the features on the left side will not be imaged. So, the side looking radar just maps only one side in order to avoid this left right ambiguity, whereas if it is a nadir looking, it will measure the entire terrain both on the left side and right side of the satellite, that will give rise to this left right ambiguity. The imaging radar itself, say the side looking radar itself, can be classified as real aperture radar and synthetic aperture radar. So, real aperture radar means the antenna length, whatever is there fixed in the system is treated as like the true length of antenna. In synthetic aperture radar, by data processing means we increase the antenna length. Increase means not physically, but electronically we increase it so that it will improve the image characteristics. We will see it in detail later in the lecture. So, it can be real aperture radar or synthetic aperture radar, that is another way of classification of imaging radar. And the radar systems can be monostatic or bistatic. What exactly monostatic and bistatic is? See, the radar itself has to produce EMR, transmit and receive back. So, there can be 2 radar antennas, like microwave I told you we may use antennas for sending and receiving the pulses, like even in passive microwave radiometry we saw we just got to know this concept of antenna is used, right. So, the antenna can be the same, like same only one single antenna will transmit electromagnetic radiation, then it will switch to receiver mode and then it will receive the signals reflected back. This is called monostatic configuration. Only one antenna is present, transmission and reception both are happening within that only one antenna. Whereas in some radar systems there can be 2 antennas in which one can transmit and one can receive. So, this kind of system is also possible, like in one of the Earth surface topography mapping mission, shuttle radar mission, there were 2 antennas. So, one will transmit and receive, one will just receive. So, 2 antennas are doing like 2 different functions. So, such systems which has more than one antenna to transmit and receive are called bistatic radars. Okay. So, but most of the satellite based radar systems are monostatic, they have the same antenna that will act as both transmitter and receiver. So, we already got to know like a very brief introduction about how a radar system works, we will just see it little bit in more detail. So, this is like the aircraft in which the radar is mounted, the radar is looking, antenna is looking like this. So, this will transmit a microwave pulse, we call it as pulse, for certain duration of time, that is let us say 10 power minus 6 seconds, something of this sort. So, this will transmit some electromagnetic radiation for certain length of time, okay. For a time period of t it will be transmitted. So, there will be one pulse in the air. So, this electromagnetic pulse it will start slowly spreading out, like once it is transmitted it will spread in terms of like plane waves, right. So, it will start slowly spreading out and it will come here. then what will happen, there are like features on the earth surface, and then at this particular instant it is going to interact with this house. Okay. So, when it interacts with this particular house, it will generate a signal here. So, this is like the reflected signal from the house at time instance 7. Similarly, there is a tree at a little bit farther distance from the aircraft. So, that radar takes little bit more time to reach this, gets reflected back, and it again moves away towards the radar itself. So, this is the return from house that is recorded at this particular instant. This will reach the aircraft first. Because of the shorter distance, this will be reflected soon and it will reach the aircraft first. So, it will be recorded here. Then the tree, which is like at a farther distance from the aircraft, it will reflect and the signal will reach the aircraft a little bit later time. So, the radar system will calculate, okay, the tree is nearer to the radar system, and the house is nearer to the radar system, the tree is farther to the radar system. So, the distance will be calculated like that, and the power will be, that is returned, will be also recorded. So, essentially a radar is a distance measuring device. It measures distance in order to map the surface that is underneath it. So, it calculates the time or it calculates the distance based on the time taken for the electromagnetic radiation to travel through from the point of origin to point of reflection and then coming back. So, before we move further in understanding the concepts of active or imaging radar, we will first get introduced to few terminologies that we use in active microwave remote sensing. The first thing is two terms known as range direction and azimuth direction. What exactly these are? Say, while we discussed about how a optical satellite like a satellite collects data in optical and linear domain, we came across two terms, right, along track and across track. Similar terminologies. Along track means is what? In the direction of satellite motion. So, in active microwave remote sensing, we call that direction as azimuth direction. So, if you measure anything along the direction of the motion of the aircraft or satellite, whatever platform, we call it as azimuth direction. The direction that is perpendicular to the direction of motion of the platform or satellite, we call it as range direction, that is across track. Okay. So, whatever we called as along track, here we will call it as azimuth direction. Whatever we called as across track, here we call it as range direction. We call it as range direction because in the direction perpendicular to the motion of the satellite, we measure the distance. Satellite or aircraft will be moving like this. It will measure the distance in a direction that is perpendicular to the motion of this aircraft. Hence, we measure the range, that is we measure the distance in a direction that is perpendicular to the direction of motion of this platform, and hence we call the direction as range direction. Okay. So, if some object is present near to the aircraft, we call it as near range, that is closer. If aircraft is here, this is the nadir point, or to represent it diagrammatically, if this is the aircraft, this is like the nadir point, okay, on the terrain. Here there is like a house, here there is another house. So, this house number 1 is at near range, it is closer to the sensor. This is at a far range. Okay. So, range, near range means closer to the system, radar system, and far range means away from the radar system. We have seen now these three terms: azimuth direction, range direction, near range and far range. Then what exactly is depression angle? So, the depression angle is the angle made by the horizontal. Say this is like the point in which the radar antenna is positioned. So, we draw an horizontal plane with respect to that point. Then say this is like a object of our interest. Draw a line from the object of our interest connecting all the way up to the radar antenna. This will form a straight line, right. Along this line it will measure the distance, say from the antenna to this object. The angle that is made with respect to a horizontal plane and this line connecting the object with the radar, we call it as depression angle. Okay. So, this is depression angle. Here the horizontal is measured like this. So, depression angle of different points are given here. So, for point N the depression angle is with respect to this. Similarly, for point F the depression angle is this. So, this is near range, this is far range. The look angle or complementary of this 90 minus depression angle is look angle, that is the angle we measure with respect to this vertical, we call it as look angle. So, here this is the vertical from the antenna. So, with respect to this vertical the look angle is this for near range point N, this is the look angle for far range point F. Okay. So, depression angle and look angle are complementary to each other. So, depression angle is equal to 90 minus look angle and vice versa. So, depression angle is you are measuring angle with respect to horizontal plane, look angle is you are measuring angle with respect to vertical line. Then what exactly incidence angle is? Incidence angle will tell us the angle at which microwave signals reach a particular terrain point. That is, let us say we have an horizontal point on the earth surface, horizontal ground. This is like the aircraft. So, this is like the radar point and this is the line connecting the radar and our object of interest. Say this is the point P at which we are interested upon. So, the incidence angle is this particular angle, theta is the incidence angle. That is at the point of our interest, like at a ground point, the angle made with respect to vertical to the ground point and the line joining the ground point and the radar antenna, that particular angle we call it as incidence angle. So, for a flat horizontal surface the look angle and incidence angle are one and the same. So, if the surface is flat, especially like if the platform especially is airborne, like we are doing remote sensing if from aircraft, then essentially the look angle and incidence angle will be one and the same for flat horizontal surfaces. If the surface is not flat or if the surface is sloping, then the incidence angle and look angle will differ. Also, like for curved surface like earth, like when you are measuring from satellite where the curvature of earth comes into picture, then the incidence angle will always be greater than look angle. Say this is like earth surface which is curved, you are measuring it from antenna from like a satellite. The distances will be huge and hence this is the point P, this is the local vertical or vertical established at that particular point. This incidence angle will always be larger than the look angle when we take into account the curvature of earth into picture. And when we are doing SAR remote sensing or active remote sensing from space satellites, when the height involved will be in the order of say 600-700 kilometers, effectively the curvature of earth will come into picture. So, the incidence angle and look angle will not be the same. And similarly, if the surface is not flat, if the surface is having a slope, then the local vertical to the point P, this is like the point P, this is the local vertical or normal to that particular point, this is the true vertical line. Okay. Say this is like the at point P a true vertical will be like this, but the normal to the surface will be like this. Okay. So, here the incidence angle we measure with respect to normal to the surface. So, the local incidence angle is this one at this particular point P. So, the local incident angle will be different from the zenith angle at that particular point. So, in order to make it clear, let us just look at this again. If someone is like, let us say we are flying like here, we are observing it from here and here there is this radar antenna. Okay. if you are like looking it from the space, you will see the straight line. This will be like the nadir point, this will be like the zenith point, right. So, if you are like looking exactly down when you are flying, so the zenith and nadir are established like this, but the normal to the surface, the 90 degree to the surface is not this vertical, this is somewhat oriented away from this vertical because the surface is now sloping. So, at this particular point the surface is sloping. So, you draw a tangent to that particular point and then you draw a 90 degree to that particular tangent in order to define the normal to the surface. So, this normal to the surface you defined by drawing a tangent, and the zenith line you define, that is by the true vertical, like if you are flying and exactly looking back, that will define the vertical line. These two will be different because of the local slope, and the local incident angle for this particular point P will be different from what you calculate from the satellite, because the terrain may be more or less flat, only at one location it can be like this. So, on an overall you can assume, especially for an aircraft platform, we will be thinking okay, the look angle theta is equal to the incidence angle on an overall picture, but these local points which are at different slopes, they can have local incidence angle that is different from this particular look angle. Okay. So, the look angle, the incidence angle that we calculated as equal to look angle, they can vary based on whether that particular local surface has any slope within it, and also for when we take the curvature of earth into picture, then definitely the incidence angle will be different from the look angle, okay, because the incidence angle are always defined with respect to normal to the surface. Whereas, if the surface is sloping, the normal will move away from the vertical, thereby changing the incidence angle. So, as a summary, in this lecture we got introduced to the concept of active microwave remote sensing, and we defined few terms that we commonly use in microwave remote sensing. With this we end this lecture. Thank you very much.